So this proportion of all the Americans who want to vote in November. Hard to know. Why is that? Too many people. I mean, this is like millions and millions of people. Is this a parameter or a statistic?
Parameter?
It's totally a parameter. It is a number that describes the population of all Americans here. The population proportion, a parameter, we're going to use a symbol like a big old capital P. So this thing is hard to know, and if you were interested in figuring out how the world works, you might want to estimate this. So if you wanted to estimate the proportion of everybody that's going to vote or says that they're going to vote in November, we're going to sample some people, and we're going to see if they plan to vote in November. Let's sample 50 people, or suppose that we did. We're going to sample 50 adult Americans, and 32 of them say that they plan to vote. First of all, do you remember what symbol we used for the size of our sample, this 50? We've used this symbol before, and we're going to use it again here.
Is it the uppercase P?
Uppercase P is going to be for the proportion of the population. This uppercase P here is this number that describes all the Americans, and that's the hard thing to know. N is what we're going to use for the sample size. We've used that before. If you see N anywhere, that's going to be talking about how many people that you sample. We sampled 50 people. 32 of them said that they will vote. So what we have is our sample proportion. Not a population proportion. We have a sample proportion. And that is a different symbol. It's still a proportion. So the symbol for our sample proportion is going to be a P, but it's going to be a small p with this hat on it. We've used that before. This is P hat. Hello, P hat. So if you see in a formula this P with the arrow above it, that's talking about a sample proportion. Is it a statistic or a parameter?
Parameter.
Well, be careful. The number that describes the entire group, like all the adults, is a parameter. P is a parameter. P is hard to know. Is P hat hard to know?
Yes.
No, it's a statistic.
Yeah, P hat it's a statistic. It's a number that describes our sample. It is a statistic. And you might see it has a little formula, which is just X over N, N being the sample size in our case, which is 50, and X being the number of people in our sample with a particular characteristic. In this case, the number of people that do plan to vote. So our sample proportion is 32 over 50, which the math is going to work out a little bit nicer if we write that as a decimal. So it's 0.64, and it's a little bit easier to think about it if we write it as a percentage. So 64% of our sample said that they planned to vote. But is that probably exactly equal to P, the proportion of everybody that plans to vote? Like, no, it's not. P hat is what's called a point estimate of P. It's just one number, and that's kind of a problem. I mean, it's not a problem, but it's likely to be not perfect in its estimation. And so what we'd want is a better, more involved method to estimate P. That's what a confidence interval is. Confidence interval is two numbers. We are pretty sure that the thing we're trying to estimate, the parameter, is between those numbers. Or it's a more sophisticated way to estimate a parameter than just giving one individual number. And what a confidence interval looks like, generally speaking, is that we're going to give the two numbers when we're done within a set of parentheses. So we give a smaller number and then we give a bigger number. And it's like if somebody asks you how many bowls of cereal you ate last year. Really hard number to know precisely. So if you just be like, oh, I ate 100 bowls of cereal, you're probably wrong. So what you would be more likely to do is say, hey, I ate somewhere between 50 and 150 bowls of cereal. It's a way for us to estimate something and be more likely to be correct, frankly. We need to find this confidence interval. There's a formula to do this. I'll give you the formula. The formula when you're making a confidence interval for a proportion always has the same format, which is you put the point estimate right in the middle. Then you see this little thing in the interval, a plus sign and a minus sign. So what that means is we're going to have to do both addition and subtraction of something that ends up being called the margin of error. And you might have seen this. I don't know if you ever read something about poll in the news, they'll be like, we thought that 60% of people plan to vote next year, and the margin of error for our poll is plus or minus 3%. And so this term margin of error, it's not just something you see in our class, it really gets used. If we're going to put the point estimate right in the middle, then if we're making a confidence interval for a proportion, that means that p hat is going to go right in the middle. And then we add and subtract the margin of error. And the margin of error has two parts to it. There's something that typically ends up being shown on the right that I'm going to just write down first. It's a big square root of our p hat again times 1 minus p hat divided by the sample size. So that's one piece of the margin of error. We have our sample size on the bottom here. We have our sample proportion appearing 3 times. Hopefully you're kind of familiar with a square root. But the weird part is what the other number that makes up the margin of error is, which in our book gets written like this. It's a z, and then there's a subscript down here. It's alpha over 2. This thing right here is the Greek letter alpha. It's the fish. So sometimes I'll describe this thing as alpha over 2. These two pieces together make up the margin of error. We know what p hat is. That's our sample proportion. We know what n is. That's our sample size. What is this z thing? Z of alpha over 2 is a percentile from a standard normal distribution. Anytime you see a z-score, it comes from a standard normal distribution. It's a percentile, and then there's a question of how the schmooly do you know what percentile it is? Every confidence interval has what's called a level of confidence. And what that level of confidence refers to is it's basically how sure we are that our confidence interval will contain a parameter. And this level of confidence is given as a percentage. There's 3 levels of confidence that you tend to see for confidence intervals. Typically, the level of confidence is 90% or 95% or 99%. Those are probably the vast majority of all confidence intervals we're going to describe as being either 90% confidence intervals or 95 or 99. So this is just all theory right now, and let's actually just make a 95% confidence interval. And then I'll show you after that how you actually find this value of z of alpha over 2. The theory can just get confusing, so let's make a 95% confidence interval for our population proportion, for the proportion of people that say they're going to vote in November. How do we do that? Well, we start out with this formula, which is our p hat plus or minus our z of alpha over 2, the mysterious thing, times the square root of p hat times 1 minus p hat over the sample size. And when I'm doing this, I write down all these values off to the side before I start doing this formula. Using our same data from before, we had our sample proportion, which was the 32 people that said they planned to vote out of the 50.64. We have our sample size, which is 50. And then for a 95% confidence interval for P, this z-score is going to be 1.96. You're like, what? Where in the heck did that come from? Well, you can answer that in a couple of ways. The first place that comes from is on page 395 in the book. They give you a little table of for different levels of confidence, they call it the critical value. I don't like that word. For every 95% confidence interval for P, the critical value happens to be 1.96. Why is that? I'll tell you in a second. We're about to jam these numbers into this formula and come up with this confidence interval. P hat, that is 0.64. The z-score is 1.96 because we're making a 95% confidence interval. And then we have times the square root of 0.64 times 1 minus 0.64 divided by 50. And the way that the math works is that you need to figure out what the margin of error is first. You need to do all this first. And then after that, you do the plus and minus. So we're going to focus on doing this math over here. And, if you're really confident about using a calculator, you could just stick all those numbers into your calculator and just get the margin of error right off the bat. I'm just going to do this in a couple of steps. One, maybe I'll do this 1.96 times the square root of 0.64, and then 1 minus 0.64 is 0.36. 64 times 0.36, 0.2304. That's just this top part here. And if I divided that by 50, I get a pretty small number, 0.004608. And I mentioned this before, but if you want to take a square root, you can also do it to the 1/2 power, which is the same thing as doing it to the 0.5 power. Or your calculator has a square root button. At this point, we need to figure out what the square root of that is. And interestingly enough, when you take a small number and you take the square root, it gets bigger. So our answer for the square root part is 0.06788. And your calculator gave you a bunch of numbers, but I tend to just round these to 4 decimal places. I feel like that is an appropriate balance of being precise, but not ridiculously so. Now we're ready to actually determine the margin of error by just taking these two numbers and multiplying them together. And when you do that, you get 0.1330.
I guess I'm kind of confused on what the plus and minus thing is.
Yeah, that's a great question. That is what's about to happen. What the plus and minus is saying, hey, you have to do both of these things. And the minus is going to become the smaller number in our interval, and the plus is going to become the bigger number. I think it'll be a little bit more clear when we just do that part. So we know the margin of error, and just as a reminder, this number in the middle was the point estimate of P. We're basically at the point where we can give our interval now. Let's actually just go ahead and say what this is actually asking you to do. And I kind of like to write these two arrows, because what we're going to do is we're going to take that point estimate. The first thing I like to do is subtract the margin of error, because that is going to be what's written first in our interval. And then we also need to take that point estimate and add the margin of error. It's like two operations. You're being told to do both addition and subtraction with this plus and minus. Our 95% confidence interval. The fancy way to write that is, okay, we're going to put the parentheses, and then the smaller number is what comes from when you take 0.64 and you subtract the margin of error, which gives you 0.507. And then the bigger number comes from when you add the margin of error, and you get 0.773. So the formula ends up producing two numbers, and the way that happens is through that including of a plus and minus. And that's, if the question on homework or a test is, hey, make a 95% confidence interval, we're done. We have the interval itself. I will say that just in terms of thinking about what this means, sometimes it's nice to translate this to percentages. If you were giving a presentation in front of some people describing this as being between 50.7% and 77.3%, makes a little bit more sense to human beings. So at this point, does anybody have any, did that help, Josh, hopefully?
Yeah, I guess I just don't know what it means. So we're between 50 and 77% sure that's true, or?
Yeah, so now the next thing I'm going to do is interpret this interval, but does anybody have any questions about the math that we just went through to produce the confidence interval? Where did these numbers come from? How did we get the margin of error? There's certainly the question of, well, how the heck did the book know that it was that much? And that's going to be the last little piece of theory that I'm going to give you. Why is it 1.96 and not some other number? Great question. So I'm like, hey, does anybody have any questions? And Josh has asked these questions, and I've been like, oh. I'm definitely going to get to both those points. I think those are both great questions. Let's just finish those things that I said I was going to do. So first of all, let's interpret this interval. This comes up on the homework. Stat teachers like to ask this sort of thing because it's basically saying, hey, what does this mean? What did we even just do? We found two numbers, but if I was explaining this to somebody, what would I say? And so that's where the interpretation comes in. And so the interpretation, in like a nerd way of speaking, starts out with the phrase, because we did a 95% confidence interval, we're 95% confident. And that's a strange phrase, I know, but it's the same thing as basically saying that we're pretty sure. We recognize that we could be wrong, but we have some good faith in the result we're about to describe. So we are 95% confident that our P, that the proportion of adult Americans, because that's what we were doing, and the proportion of them that plan to vote is in this interval. And I could write it in a couple of different ways. I'm going to give the percentages because I think they're the most straightforward way to talk about this. Is we think that proportion is between 50.7% and 77.3%. And, is it possible that the proportion of adult Americans that plan to vote is not between these numbers? Yes, for sure. We trust the science, assuming that we took a good sample. We're pretty sure that it's somewhere within this range. So that's kind of what the confidence interval does. It gives you some idea of the accuracy of P hat. We're not really super accurate here. There's a 27% range in this confidence interval, but I think it's somewhere in there. I know that everybody's like, well, why is Z of alpha over 2 1.96 for a 95% confidence interval? Where this thing comes from is, well, first of all, it's from standard normal distribution. The first thing that I like to do when I think about how you come up with this, besides just looking at the book, is to draw a standard normal distribution, to draw a mound that has a middle of 0. So here's a standard normal distribution. I'm going to go ahead and put my mean right in the middle. And let's look at for a 95% confidence interval. So what happens is that there's a middle 95% of this distribution. And what that z-score is it's the border of that middle 95%. And so, this is really all you need to know in order to find this number. Is you need to understand that because we're doing a 95% confidence interval, it's the boundary of the middle 95%. But there's a little bit more to it, and another thing that will make this number a lot easier to find is to recognize that if there's 95% in the middle, how much is just in this pink area, just in this lower region? And so if there's 95% in the middle, then on both outsides, there's the rest of it. There's 100% minus 95%. So there's 5% in total on both outsides. But what we want to know is how much is just in this lower region. So because there's 5% in both outsides, there's half of 5% in this lower region, which means that there's 2.5% in this pink area here, which means that for a 95% confidence interval, Z of alpha over 2 is the 2.5th percentile. So to find this number, like where the book would get this number from, is they need to know how you find the 2.5th percentile of a standard normal distribution. Anybody know how you find a percentile of a standard normal distribution or any normal distribution?
You do
Would this be the
second thing? Second vars and numbers in?
Yeah. Second bars, but then you got to do something before you get to the part where you get to put the numbers in. The second bars has a big long list of things.
Is it inverse norm?
It is inverse norm. Yeah. The two that you used in chapter 7 our normal CDF and inverse norm. So because we're trying to find a percentile, we're going to use inverse norm. And inverse norm needs 3 numbers, which depending on your calculator, your screen will look different at this point. But you need to know the area, you need to know the mean of the distribution you're working with, and the standard deviation. We're trying to do this for a 95% confidence interval. And so we found out that the percentile we want is the 2.5th percentile, but you can't put 2.5 in here. You need to change the percentage to a decimal. That means you're going to put 0.025 as the area. We basically just took 2.5% and turned it into a decimal. And then the mean, what mean? You don't know that. Mean is 0. Standard deviation is 1. And when you do that, you get a bunch of numbers. Negative 1.95996396. And if we were really worried about accuracy, you could use all these digits, but that's kind of ridiculous. We tend to just round this to 1.96. And you might notice that this number, the 2.5th percentile, is negative, but it turns out that because we end up adding and subtracting, you can also use the positive equivalent, the upper boundary of this middle 95%, and it doesn't change your answer at all. And I tend to just use the positive value because it's just one less thing to worry about. Can certainly use the negative number if you want, but either way, if you use negative 1.96 or positive 1.96, you would still get the same confidence interval we got earlier. So either it's like, oh, that was so easy, or what the heck just happened? Does anybody have any questions about why this is 1.96? Is it going to be 1.96 if we use a different level of confidence? Let's say it's your test and your teacher has given you a different level of confidence, not one of the easy ones that's on page 395. Let's do like I don't even know what. Does anybody want to just pick a number, some different level of confidence? That should be kind of high. I mean, it'd be silly to make a 5% confidence interval. I mean, you'd be like, hey, I have very little confidence in this.
93%?
90, yeah, let's do 93%. Sure, I'm down with that. We're going to make a 93% confidence interval. Our middle region is not going to be the middle 95% anymore. It's the region that corresponds to our level of confidence. So we're going to make a 93% confidence interval, which means that we're going to have the middle 93% here. How much area is going to be in just this lower portion then?
3.5%.
3.5%. Perfect. Because we're going to take that total area on both outsides, that's 7%, divide it by 2, and we get that there is 3.5% in just this bottom part, which means that the z-score that we use for a 93% confidence interval is going to be the 3.5th percentile, which means that we can still use inverse norm, but instead of using 0.025, we need to put 0.035 here. And what do we get for if we're making a 93% confidence interval?
Negative 1.8119.
Yeah, that's what I'm getting right. That's what I'm looking at on my calculator. When I use inverse norm with these 3 numbers, I get negative 1.81910674. Good Lord, that's a lot of numbers. But if you round it to 2 decimal places, you get negative 1.81. So that's this lower value here. If I was doing a formula for a 93% confidence interval, I would use positive 1.81. If that bothers you, just stick with the negative number. You see it a lot in like news and stuff. They'll report a value and they'll also include the margin of error. And when they do that, they're really saying an interval. They're saying that, yeah, we think that our estimate is not perfect, but we feel better about giving you this estimate plus and minus a margin of error. Are there any other questions about what's the purpose of a confidence interval? I mean, I think that's a really great question, because if you don't understand something's purpose, like why the heck would you ever even do it?
Where'd you get the 7% for the second part?
Okay, we were like, hey, let's do a 93% confidence interval instead. We need to know the value of Z of alpha over 2 for that 93% confidence interval. The Z of alpha over 2 is the border of the middle. In this case, it's going to be the middle 93%. If there's 93% in the middle, it means that there's 100% minus 93%, 7% on both of the outsides. In this upper portion and in the lower portion has a total of 7%. The 7% came from taking the level of confidence and subtracting it from 100%.
Oh, okay.
But you don't end up putting 7% in inverse norm, because we want the half of 7%, the 3.5th percentile, because 7% was the total area in the outsides, and there's half of that in just one side, which is how we came up with the value of 0.035 to put in inverse norm. So pop quiz, every time you get a different level of confidence, do you have a different Z-score to use in your interval? Yes, perfect. Harder question, is the Z-score for a 93% confidence interval for a population proportion always going to be negative 1.81? Or might it be different sometimes if it's a 93% confidence interval?
It would always be that 1.81.
It would, yeah, exactly, yes. For 93%, this is Z of alpha over 2 for every 93% confidence interval for a population proportion. It's true that if you have a different level of confidence, you get a different value of Z, but for a certain particular level of confidence, the Z-score is always the same. And that's fundamentally what you need to know in order to come up with a confidence interval. We need to be able to use this formula, which has these three pieces in them, p hat and our sample size, and then that Z-score. And two of them are fairly easy to get. The p hat and the sample size should come from reading a particular problem. But then the Z-score comes from understanding that you're trying to find a percentile, or maybe just looking at page 395 of the book if you're doing one of the more standard levels of confidence. Here we go, another question. Is it possible that the proportion of all Americans that are going to vote is not in this interval? Is it possible that the proportion is 45%?
Yes.
Yeah. Another question. Do we ever know for sure whether it's in our interval or not? No, we don't. Because we don't know P. We don't know the true proportion of everybody that plans to vote. We'll never know that. Nobody knows that. So we do science to estimate it. Let me just talk about the level of confidence for a second. If you were looking at, say, two different confidence intervals, how might they compare? Say you were doing a 90% confidence interval versus a 95% confidence interval. So a metaphor that I like to use is our parameter is like a fish, and the fish is swimming around in a big ocean, and our confidence intervals are nets we use to catch the fish. And a 95% confidence interval has a higher level of confidence. And if you want to be more sure that you catch fish, what sort of net should you use? Maybe that was a bad question. Okay, a different way. You have a tiny little net or you have a huge net. Which net are you more confident will catch your fish? The tiny one or the huge one?
Huge one.
The huge one, right? No duh. For a higher level of confidence, your interval ends up being wider. You're more confident it will catch the fish. Not higher, but wider. What I mean is, for example, say you had a 90% confidence interval P, and I'm just going to make one up here really quickly. Say that interval was from 50% to 60%. The width of this interval is 10%. That's what I mean by the wideness of it. But if you were going to do a 95% confidence interval, you still put p hat in the middle. So it's not that a 95% confidence interval is higher, it's just wider. So you might see something like this. Instead of from 50 to 60%, you might see from 45% to 65%. So basically, as your confidence level goes up, the width of your interval goes up. I can give you right now a 100% confidence interval for the proportion of people that say they're going to vote in November. I'm absolutely sure that this interval attains that proportion. I'm not wrong, I promise you. Here's my interval: 0 to 100%. Am I right? For sure. But is that useful at all? No. That would be like if you told the police that you're pretty sure the robber was less than 20 feet tall. I mean, you're right, but you haven't given them any useful information. Having a level of confidence that's something like 90% or 95% is giving a trade-off between an interval that's useful but also pretty sure about. And if you want to see this exact idea again, I have 2 videos on each of these sections. One of them is a little bit longer and involves some theory. If you're like, I just want to see how to do it. The second video is me pretty much as quickly as I can, just going through another example of finding a confidence interval, finding all the pieces and putting them together and arriving at the final interval. More fun for all of us if we were in a classroom, but and as always, if you have any questions, please feel free to email me. I'm happy to talk about things over email or even like have a chat like this. Thanks for coming. Hope it was useful.
Thank you.
Yeah, of course. Enjoy the rest of the day.
Thanks.